Good morning, everybody. Great to see you all here this morning. Thank you for participating in this workshop. I'm really delighted to welcome you all. This is a first virtual workshop on low temperature geothermal that we are hosting, led by Professor Yufeng Lin and IWRC, who've taken the lead in organizing this workshop in partnership with the Institute for Sustainability, Energy and Environment, or iSEE, and Facilities and Services, or FNS, on campus. The geothermal research and application on our campus is great in that it's bringing together researchers from diverse parts of our campus, including scientists from the Prairie Research Institute, the faculty from the Department of Civil and Environmental Engineering, and practitioners from FNS. It is also an excellent example of the idea of using our campus as a living lab and a test bed for developing and testing new technologies that can then be scaled up to real world application. And it's great to see such a diverse group of scientists, engineers, practitioners, decision makers, and stakeholders here today to discuss the opportunities for low temperature geothermal as we move forward towards looking at alternatives for reducing our dependence on fossil fuels and moving towards a cleaner energy future. For those of you that may not know iSEE, our mission is to promote interdisciplinary research, education, and teaching on campus. We are also responsible for strategic planning for campus sustainability, which includes the development of our campus's 5-year climate action plans. The latest climate action plan is ICAP 2020, and that was just launched on October 20th this year. This plan makes a commitment to achieve carbon neutrality on our campus no later than 2050. And geothermal energy is one of the pathways that we want to explore in trying to make our campus more sustainable. iSEE also works across the state with the Illinois Innovation Network that consists of all the public universities in the state of Illinois in order to provide our university's expertise and experience in sustainability to all public universities in the state. And above all, iSEE coalesces research communities to pursue innovative research themes. We are delighted to join Yufeng in hosting today's workshop. It looks like a great program of topics and speakers. I'm looking forward to the presentations by the experts from our campus, as well as from the national and international organizations that have taken the time to join us today. I wish you all a productive morning, and I'm looking forward to the talks. So let me turn it back to you, Yufeng.
Thank you very much, Matthew. And this is a great opening for us. And without further ado, I want to introduce you the first speaker, and it's Dr. Atala. And Dr. Atala is our executive editor of Campus Facility and Service. And without further ado, Atala, the floor is yours.
Sorry, I was muted and I was talking for some time. So
now we hear you.
My apology. What I was saying is thank you, Dr. Lin, for the introduction, and thank you, Dr. Kana, for organizing this event. We at Facilities and Service are very happy to be an active participant in promoting and advancing the university research mission, and to also promoting and advancing sustainability. In this presentation, my colleague Morgan White, our Associate Director of Sustainability at Facilities and Service, will join me in this presentation. And we will talk about 3 topics. We'll talk about climate leadership commitments, Illinois Geothermal Coalition, where my colleague Morgan will speak about this, and then I will present to you examples of the geothermal projects that have been implemented on campus. And at this point, I'd like to turn it over to my colleague Morgan.
Thank you, Mohammed. So I will just do a very quick rundown of the climate leadership commitments. Madhu has already given you a quick overview of our strategic plan, but let me tell you how Facilities and Services ties into that. Facilities and Services is actually the folks who maintain and build and operate the physical plant. So we handle several aspects of the campus, including waste management, energy production, and the transportation network. These are just some of the images, and you see some of our folks here are there with their masks, and we are very excited to be involved in the geothermal efforts. For the campus as a whole, we've signed 2 climate commitments. One of them is called the carbon commitment, which is that we will make our campus carbon neutral as soon as possible, and we have a deadline that we set of 2050. And then we also signed an agreement with the community, or to work with the community to build resilience here in town with Champaign-Urbana and Savoy. That strategic plan for how we're going to achieve these goals is called the ICAP. And as Madhu said, the current one is called the ICAP 2020. And if you want to know some details about that, you can visit the ICAP portal here at this link, and I can put that in the chat in a little bit here. It's organized into various themes, and we cover all kinds of different topics. But of course, today we're focused on energy. One of the primary focuses for us at first has been clean power, and that includes solar. And we have an existing solar farm. We have a here we go. We have a second one under construction. This is one of the latest photos if you want to go visit it in the South Farms area. And we're also in conversations about a larger scale off-campus solar agreement that would get us almost 1/3 of clean power. This is for electricity. Now, we have a wind agreement too. But all of that is really in the electrical sector, and we really need to move into geothermal. So how did we get to this point? Well, the 2015 ICAP had this chart that showed what we could do to reduce our emissions. And you see geothermal's out here at 2035. And it was actually at this great event called the Campus as a Living Lab Workshop that we talked about what we could do to connect research with campus sustainability and the physical infrastructure. And it was Dr. Lin who pointed out, why are we waiting to 2035? We need to start now. And so since then, we have had this momentum growing about geothermal. And one of the things that we'd like to point out, and if you want to grab your cell phone and pick up the QR code here right now. Oh, it's not going. I see. There we go. Here's the graph. Sorry, folks, that's dual monitors. Okay, if you want to join the coalition, here is the QR code or this link. We're also going to show this at the end of the event this morning. And what we're looking for is anyone who's interested in helping us build and strengthen Illinois as a leader in geothermal for research and installations. We are very excited about it. And now I'll shift us over back to you, Mohammed, for geothermal projects.
Thank you very much, Morgan, for your great help. In the next few slides, we'll go through some of the samples of the projects. As you see here on this slide, the chronological progress over 10 years between 2010 until now of the projects. You see that from 2010 to 2016, projects were implemented, and we will go through that in a minute. In 2017, we have, can we please mute? We will have the campus as a living lab workshop that Morgan just spoke about. And then from 2018 to 2020, we had 5 projects, and we'll go through this now. Next, please. Well, the first one started in 2010, the fruit farm admin building. That was a capital project, 66 square feet, energy upgrade. And the system included a horizontal loop supplied with glycol connected to 5 ground source heat pumps. This project, in the last 5 years only, the energy use intensity has been between 20 to 25 kBTU per square foot, which is 3.5 times less than similar buildings. Great result. Next, please. In 2011, in Allerton, the Evergreen Lodge, it's a 2,800 square feet building. Again, an efficient HVAC system was upgraded, and the project included about 6-ton geothermal with hot water generator, geothermal loop, and 200 feet deep boreholes, 410 vertical loop. The cost for this project was about $28,000, and the annual saving $2,000 per year, which is a payback of about 14 years. And some of our colleagues involved in sustainability, they believe that payback 14 years is kind of long. However, for this great technology and its sustainability and reduction of the carbon footprint, we believe it's a good period. Next, please. In 2014, and again at Allerton Park, the Gate House building, another HVAC system upgrade, 7 300 feet deep boreholes were utilized with 7 water source heat pumps. This project, our analysis shows that it reduced the on-site emission by 10.4 tons of CO2 per year. Next, please. 2016, we had this revolutionary project, if I would say, where the project installed geothermal loop with fiber optic cables in 330 feet deep borehole and instrumented with a thermal response test. And the main focus here was to collect data to form a baseline, to collect baseline subsurface thermal data to be able to optimize geothermal energy. The status quo before that was we as engineers, when we design geothermal field, we have our preset criteria and data, generic data, and we design based on that. This project aimed to see that let's discuss the subsurface condition in a specific site and see how that could optimize the design, which in my opinion, as I said, it was revolutionary in nature, and it was used as we see in the next slides. And sorry, yeah, and I was going to say this past project led actually to the implementation of some student project, and it was led with Professor Len and Professor It was a great work. In 2017, iSEE the Living Lab Workshop, and Morgan did speak about this, and I will not talk about it again here, but moving forward, in the 2018, the monitoring well on Bardeen Quad was implemented. We were planning for the campus instruction facility as a project, and here we did learn from the project that I just spoke about in the farm, in the energy farm, and we felt that it would be great to perform this work here, to have a test well, to be able to understand the subsurface condition of this specific site and to be able to optimize our design. So FNS and iSEE funded the installation of this work, and again, our researchers on campus did work on it and did very good work and provided a lot of interesting data. And the studies output utilized in the design and optimizing the design for the SIF building. Next, please. So that happened in 2019, the campus instruction facility, or as we call it, SIF. And the geothermal here, the system will supply approximately about 135 tons of heating and cooling capacity, which is about 65% of the total building demand. And our estimated reduction in GHG emission by about 70% compared to a similar size building. And also the system was designed to enable expansion, and also the system designed to achieve LEED Gold. Next slide, please. So adding a geothermal system to this building will save about $45,000 per year of the operation of the building. And if we project that to 30 years, that's a very good amount of dollars here, about 1.35 million. And measuring the ground thermal properties, the fact that we did the test well to optimize the installation, as we said, have helped us to reduce the number of boreholes needed from 60 to 40 at 450 foot deep. The monetary savings from drilling 40 instead of 60 have reduced again the payback in this project from 40 to 28 years. So we can see here, excuse me, a live experiment that research adds significant value to optimize design and enhance efficiency of a geothermal project. Next, please. 2019, the Hydro Systems Energy Piles, another research collaboration on campus here. We use 50-foot deep concrete piles already being installed for the integration of geothermal heat exchangers within the foundation. As you see on the right of the screen, the top, you see a building on the right and a bridge in the middle of the screen. The foundation below the bridge, the bridge foundation is carried on caissons, concrete caissons that are drilled 50 feet deep, already drilled. So we worked with Dr. Tucci Pasher, who is leading this research in the picture on the right below, with our colleague Morgan White, looking at those piles. So this innovative approach is about 30 to 40% cheaper than conventional methods of geothermal system. The project estimated to supply the Hydro System Lab with about 515 million BTU per year, and annual reduction in greenhouse gas emissions of approximately about 100 metric tons. And obviously there will be continuous, in addition to the operational value, there will be also research value, continuing to conduct research and collect data on this concept. The project cost was about $240,000, funded by Facilities and Service, iSEE, Civil Engineering, and the Student Sustainability Committee. Next, please. This year, we did the RIPE greenhouse and the head house. Greenhouses, as you know, consume a huge amount of energy for cooling. So a geothermal field was a very good choice there. Geothermal system is designed to maintain constant environment condition, 83 Fahrenheit for the greenhouse and 75 Fahrenheit for the head house building. And it included 3 heat pumps and about 32 vertical heat exchanger in 300 deep boreholes.
Just wanted to let you know you have about a minute left for that one, this presentation.
Next slide, please. The Gable House ongoing project. So that's happening right now. The Solar Decathlon is a student-led design build competition. So our students in their design incorporated incorporated geothermal field to enhance the energy. The project included fiber optic cables as well in the loops. It's 150 feet horizontal loop at a depth of about 5 feet, and also utilized geopolymers as a substitute for concrete. Next, please. And thank you. We appreciate that, and we completed before the 1 minute that we were given, so it's good.
Yeah, thank you, Mohammed and Morgan. Next up, we have Ryan Daugherty introducing the geothermal heat pump and industry landscape.
Sorry, needed to unmute. Good morning, everyone. Thanks so much for the opportunity to present this morning. It was about 2 years ago that I had the pleasure of visiting the UIUC campus and meeting Dr. Lin and his colleague Andy. And I was able to tour some of the projects that Dr. Atala just presented. And it was a very eye-opening day for me because I didn't realize that just up the road from where I am here in Springfield, Illinois, at my alma mater, they were doing so much groundbreaking, pardon the pun, research on geothermal technology. So I'm really pleased to see this coming to fruition and this working group really taking shape. I am the Chief Operating Officer for the Geothermal Exchange Organization, also known as GeoExchange for short. And we're a national trade group representing the geothermal heat pump industry, the manufacturers of heat pump equipment, component manufacturers, all the way through the supply chain to the contractors who install these systems, the drillers that put the ground heat exchangers in the earth, component manufacturers, designers, architects, the whole gamut. So really our focus at GeoExchange is really 4 pillars. We're very active in Washington, D.C., where we work on a number of policy issues. We're involved in public outreach and trying to raise consumer awareness of the technology. We seek to engage in partnerships with like-minded organizations. And we're also very focused on ensuring quality standards, because quality in the design and installation of these systems is of the utmost importance. So we're very happy that the US Congress has seen fit to incentivize the adoption of geothermal heat pump technologies, along with a range of other renewable technologies. There are currently existing credits for the installation of both commercial and residential installations, which has been a major driver in the adoption of geothermal heat pumps, because the cost associated with installing these systems is higher due to their nature, the fact that you have to drill and install pipes in the ground to make them work. The higher upfront cost is a major impediment and a barrier to the broader adoption of the technology. So the tax credits have been fundamental in assisting with the broader deployment. We are currently seeking an extension of the credits, which are currently phasing out. They had been 30% at the residential level last year, and have now dropped to 26% this year. They'll go to 22% next year without any action on the part of Congress, and then expire permanently in 2022. But we're not going to let that happen. We've got some good compatriots in the solar industry and a number of other renewable energy industries. And we feel that we've got a really good shot at getting these extended, which is going to be important as America really charts its clean energy future. I mentioned, our activities and actions at the federal level. I do want to highlight this report that came out of the Department of Energy's Geothermal Technologies Office last year. You're probably all familiar with it, but if you're not, I would urge you to Google it, because it really, in my mind, is the roadmap for the future of our industry and the other geothermal technologies as well. As it sort of identifies the future for geothermal heat pumps, it projects the potential for a 14-fold increase in existing and installed capacity, which would be the equivalent of about 28 million residential homes in the US. This is a really staggering jump or leap forward for us in terms of the potential. This is not going to be easy to do, but the GeoVision report really lays out a bit of a roadway or a glide path to achieving that lofty goal. And those of us in the geothermal heat pump industry are absolutely dedicated to seeing this vision become realized. And this working group at the U of I is one of the key ways that we can do this by a collaboration of public institutions, private industry, and government. We're going to be able to achieve this vision. There are a number of barriers, and some of them are identified in the GeoVision report. It doesn't go into depth on one bugaboo, I'll call it, which really it sticks in my craw a little bit, and that is the technical reference manuals, or some states call them technical resource manuals. These are really the guiding documents that outline how investor-owned utilities are able to craft and implement their energy efficiency programs. Well, there are about 32 of these TRMs around the country, and they basically have a number of calculations about what are cost-effective energy efficiency measures. We weren't at the table when many of these policies were crafted, so this is something that is near and dear to my heart, and we've been very successful in Illinois in working with the stakeholder advisory group that's organized through the Illinois Commerce Commission to address deficiencies in the Illinois TRM. We're working now in Massachusetts and a number of other states to address this, but this is one of a variety of barriers to the adoption. I mentioned higher first cost, low natural gas prices, low consumer awareness are other barriers, but the industry is working diligently to overcome them. I mentioned consumer awareness. We are currently promoting a Geothermal for All campaign. You can learn a little bit more about this at geothermalforall.com. And it's kind of an amusing, there's a number of videos that we shot to go with this campaign. If you put Geothermal for All in YouTube, you'll be able to see some of that. And it really kind of promotes the fact that geothermal heat pump technology appeals to people across the spectrum, whether you're doing it because you're environmentally conscious and want to have the cleanest heating and cooling technology, or you just want to save money, and that's the most important driver for you. Geothermal heat pumps can really appeal to anybody. I know I'm getting close on time here, but I do want to highlight a very important development in the geothermal heat pump industry, and that is the International Ground Source Heat Pump Association, which has always been a sort of a counterpart of ours. They're focused very much on training, standards, research, accreditation, and certification. They have now come over from their former home at Oklahoma State University to GeoExchange, and we're now partnered. There's a bit of a merger. They're retaining their branding and some oversight, independence oversight, but there's a bit of a unification now and a much stronger tie between the two organizations. So we're very hopeful and optimistic that this is going to pay great dividends for the industry. What does the future hold? Well, on the left of your screen, you'll see some reports about electrification of buildings and building decarbonization. These all came out in 2018, which was the year of the electrification report. That 2018 is where building decarbonization and beneficial electrification really took hold in many people's minds, and we're starting to see the electrification movement really charge forward. The Building Decarbonization Coalition is in California, but just recently the Midwest Building Decarbonization Coalition sprang up, and I think it's going to be very important for us to work with such organizations to really drive building decarbonization.
Okay. I think
one last thing,
the
advent of the commercial ownership and the third party sort of all geothermal community is really taking hold. We're starting to see more and more geothermal communities around the country. One very important one is in Austin, Texas, Whisper Valley. And I would urge you to plug in Whisper Valley to YouTube or Google and learn a little bit more about this. This is really the neighborhood of the future, and we hope to see many more of these replicated. I think I'm about out of time, so I'll end it there. And thanks so much for allowing me to present this morning.
Yeah, thank you, Ryan. Next up, we have Martin Forsen introducing the market transformation of the Swedish geothermal heat pump market.
So, sorry, it was a little bit slow there to unmute myself. So, good morning everyone for you. I'm calling in from Stockholm, Sweden. And I'm very happy to be here. Thank you for inviting me. I'm very honored to be given this opportunity to give some views on the market transformation of the geothermal heat pump market in Sweden specifically. So I work as Manager International Affairs for the heat pump manufacturer NIVE in Sweden. I am very active in different associations related to the heat pump technology, not only for the geothermal heat pumps. I am the serving president of the European Heat Pump Association. I'm also a member of the board of directors for the GeoExchange Association in the US. Of roughly 10 million people. We have around 2 million single family houses, and the stock of geothermal heat pumps now in service in Sweden is a little bit more than 500,000 units in operation. So I believe that we have the highest concentration of geothermal heat pumps, I guess, worldwide. And just some quick facts about the technology and the costs related to it here in Sweden. Just very, very rough numbers. In average, the total investment cost for a geothermal heat pump installation for a single family house is roughly around $15,000 US. And that includes everything, the drillings and the appliance itself, installations, everything. The drilling cost here in Sweden is roughly around $11 per foot. And what makes the drilling a little bit cheaper here, much cheaper than in many other countries in Europe, is that typically no backfilling is required here. We have very solid bedrock, granite and gneiss, most all over the country. So typically no backfilling is required by the authorities. Typical drilling depths for a single family house is somewhere in between 600 and 900 feet. And the cost of electricity for the end users is around 16 cents per kilowatt hours, everything included there as well in that price. This is a picture of one of the suburbs just outside Stockholm. I live not far from here. So on this map, you see the small brownish dots here. They're actually houses. And then you see the streets, and then you see some green squares. And all these green squares are drillings for geothermal heat pumps. And this is taken from an online tool. You can also, you yourself, you can go to this website. You see the address at the bottom of this slide. Here, blue squares. Those blue squares are water wells for drinking water. But this is the way it looks like all around the big cities. We have a very high concentration of geothermal heat pumps around the big cities especially. So this graph here shows the market development for different types of heat pumps. So the reddish bars here depicts the annual sales of geothermal heat pumps. The blue ones depicts the sales of air-to-water heat pumps, and the green ones exhaust air heat pumps, which is a little bit of a special product here for Sweden, which is mainly used for new construction of single-family houses. And that was introduced in the late 1980s. and has an extremely large market share for new construction of single-family houses, low-energy houses, where typically the energy demand is not high enough to economically motivate installations of a ground source heat pump. So typically we have worked with retrofit installations, replacing old oil boilers mainly. For Sweden and in general, we used to depend to around 70 or 80% solely on burning oil, heating oil. There are really no gas grids available, so we do not use gas for heating, which is a little bit special for Sweden. We do have quite a few buildings that are using electricity, direct electricity and electric boilers as well, but we are actually retrofitting them at a very high pace. So you see here for the geothermal heat pump market, it took off in the late 1990s, and then it sort of boomed in the early 2000, and then it stabilized and it got saturated towards the last couple of years. But if we would like to talk a little bit about the market transformation and look at it from the view of a product life cycle curve, you know, these different phases of the product life cycle. We have the introduction phase. And in the introduction phase, it's typically characterized that there are a few manufacturers on the market, small manufacturers, few retailers and installers, typically poor profit and poor competition, and quite a lot of lack of technical know-how. If you look at the customers, you typically see in the market introduction that they are sort of overrepresented by retired engineers who find this technology interesting. The customers are few, there are early adopters, and they do, because of their interest, invest in this fairly expensive products. And in general, it's very poor awareness around the general public and policymakers and all over. So this is the time where the industry needs to build up some kind of an industry infrastructure. A good idea here is to form some kind of an industry association so that you can join forces and address the policymakers and the public in terms of disseminating information about what this technology can bring to the
Just a reminder for a 1-minute warning.
Okay. All right, so the market activities at this point of the stage would be to find, from my perspective, look for strategic allies. Specifically, it's a good way to work with electric utility companies that could benefit for this development as well. And now we spent a lot of time in my last minute only on the market introduction, but maybe it wasn't so bad, because this is where I believe that we stand to a large extent still somehow in the US. We need to kick off and get into the growth area of the market. And that is sometimes fairly difficult to get into the growth phase. Sometimes you need some kind of a trigger factor to help you overcome that barrier. That could be in terms of a subsidy scheme or tax credit scheme. We put a lot of hope into that. It could also be some kind of a technology procurement program offered by the authorities or something. Be stimulated by a change in the building codes and legislation. And by that, I think my 1 minute is over, and I'll have to stop there, even though my presentation is not really fully over. Thank you anyway.
Thank you, Martin. Hopefully we'll have a chance afterwards to go through some more questions and share all of the presentations. So for slides that you haven't gotten to, that'll be posted. Our next speaker is Timothy Stark with the numerical modeling and validation of geothermal systems.
Okay, good morning, everyone. I'm here with Jala Lin and Abdulkader Idris. We're going to talk about some of our numerical modeling of some of the projects that Dr. Atala started us off with. So I'll kick off the first two and then I'll turn it over to Jala and Abdul Qadir. So here's the list. I'm going to talk about the gable solar house, shallow geothermal system, and the energy shaft at the energy farm.
Yeah, Tim, I don't think we're seeing your slides. Over.
Oh, well, sorry about that. Just a sec. There we go.
We see them now. Thank you.
Great. Okay, yep, there we go. Okay, so there's the list. So here's the solar house at the energy farm, a fairly shallow geothermal loop, and this loop is augmenting the solar system in the house. And so we're interested in looking at very shallow geothermal modeling for this system. There's the installation and heat pump going into being installed in the building for this loop. Now I'd like to shift over to the energy shaft. Dr. Atala started talking about the boring there at the energy shaft. That boring is in the little shed here. And so we installed an energy shaft right next to the boring. It's 30 feet long, 2 feet in diameter. And that allows us to calibrate our model with the energy being measured in the boring. And then we can also introduce heat or different temperatures either through the shaft or the boring and see what the heat transfer or energy transfer between the ground and the energy shaft is. Here's a look at the energy shaft and the loop inside of it. There are fiber optic cables inside the shaft, as well as the boring to help us with our calibration of the numerical models. Okay, I'm going to shift over to Abdul Qadir, who's going to talk about some of his testing on the effects of heating cycles on drill shaft capacity.
Good morning, everyone. Oops. Good morning, everyone. So I'll be talking about the part of my master thesis data that we are using for the energy shaft as well. So we use the large direct shear test, which is 12 inches by 12 inches by 8 inches direct shear test to simulate the clay, concrete, or the pile clay interface for interface of friction angles and shear strength parameters. So we had the concrete block in the lower shear box and the clay in the upper shear box. The upper shear box right side was replaced by another side to accommodate thermocables, and this is the entire setup of the experiment. So here we have two heaters, two cartridge heaters that are heating the water, and the water is connected to another water pump that will circulate the water to have fully saturation condition, and also to facilitate heating and to make it easier. We have the heaters connected to a temperature controller, so we can just put the temperature that we want, and a data logger that is connected to the thermocables for us for the temperature, for controlling the temperature for all the thermocables. Oh, okay. So yeah, so here I will just present the summary of one of the soils that we tested. It was a low PI at different temperatures. So the main idea was to test under a heating cooling cycle from the room temperature to a certain temperature, which is 40 Celsius, 55, and 70 Celsius, then back to the room temperature, and then shearing, and compare the results with another test under this the same normal stress without heating condition. Another phase in this experiment was the same temperature, but with a different number of cycles. So we did under 1 cycle, 4 cycles, and one of the tests was under 9 cycles. Here we can see at the right figure, we can see the volumetric response under heating, which was after the primary consolidation. It agreed with the literature for normally consolidated clay. We have plastic contraction up to the during heating and at the same temperature. and this contraction is irreversible. So when we go back to cooling, it still undergoes some contraction, but it's not as much as heating. So this induced contraction made the soil more stiff, which obtained or gave us more shear strength. As we can see here, the shear strength increases with the number of cycles and also increases with the temperature. So that's mainly my presentation. I will go switch now to my colleague Jala.
Okay, Jala is going to talk about two projects. First, the deep direct use project, and then the Granger engineering quad that Dr. Atala mentioned.
As you can see on the left side, basically it was the soil profiles on deep direct use well bores. The well bore was around 1900 meters, which passed through 15 soil layers. On the left side was the asymmetric boundaries. Basically, want to model the cylinders of this model, and on the tops and bottoms they used the constant temperature, reflect the initial temperatures on the site. On the right one, we use the linear initial temperature first, then to do the static analysis to get the temperature profile over the ground surface, over the ground depth. Then on the right side, you can see the zoom-in pictures for the tubings and the casings more directly. In the flowing analysis, we want to verify the tubing and the annual space and the grout to check which method will preserve heat more in the flowing analysis. We simulate scenarios consider flow rate and the properties of the wellbore components. And here is our result. Overall, basically, you can see there's few heat loss during the ejection from the Mount Simon layers. And then overall, the temperature decreased around 2 Fahrenheit. And for silica foam serves as a better isolation material to preserve heat. And the temperature loss will be less if you have a higher ejection rate. Then we switch to for the injection wells. Based on the temperature difference between the injection temperature and the average temperature of the soil profile will influence the temperature at outlet linearly. Then we switch to Granger wellbore field modelings. For this site, the red color here basically shows the drilling of the one borehole. Later, we'll measure the temperature data on this borehole and to compare with the simulated result. Here's the configuration of the well group on the site. Basically, there's 40 wells being installed on the site. And you can see on the figure, there's green tunnels and the pipes running for around 140 years. These tunnel and pipes provide actual heat source to heating the ground. And we want to get the initial ground temperature contours by considering the heat from this pipe and tunnels first. For this scenario, we run a stack analysis without considering the tunnels and the pipe. And after that, we set the tunnel and pipe at constant temperature for running for 140 years, get the ground initial temperature. Later, with the configurations, we compare the data from the measured data, green and the red line here, and the dash and the orange line, blue and the red line here to show the model result. All the measured data and the
Just a reminder for your time.
Simulated data pretty well. As you can see here, in the summertime, they will reserve some heat in the ground and the heat during winter. Overall, when we have a high injection rate, the temperature increase will be less than 5 Celsius. Okay, that's all. Thank you.
Great, and thank you. So we've got about 30 seconds left. And so the measured data is coming from the borehole that Dr. Atala mentioned in the Granger engineering quad. Thank you.
Thank you. Our next presenter is going to be Corinna Absurd, unlocking the potential for the geothermal energy in the UK, ABGS perspective.
So I'm just getting ready. Great. Thanks very much for inviting me to attend this workshop. My name is Kurna Abasa. I'm leading the geothermal energy research at a British Geological Survey in the UK. So I'm presenting to you from Oxford, where it is the afternoon. In my presentation, I would like to briefly run you through the geothermal resources that we have here in the UK, which are very different from what you have in the US, and then see how, and then show you how some examples of how my team is sort of trying to unlock the potential of these geothermal energy resources in the UK. Now, the UK is sited on relatively stable continental settings, so we don't have any high enthalpy resources associated with continental margins as you do in the UK, also tectonic plates. However, there is still some low to medium temperature geothermal resources available, and these could actually make a significant contribution to the decarbonization efforts of the UK. The principal sources can be classified into sort of 4 categories, which then can be further divided into shallow and deep sources. So that the first type, hang on, I'm pressing the wrong one. The first type of the resource is associated, it's a traditional hydrothermal systems in deep onshore sedimentary basins. The hydrothermal reservoirs that we are currently exploiting with one scheme are sort of the Permo-Triassic sandstones, and so there's one scheme down in the south of England, and the Permo-Triassic sandstone are shown here in orange. And another resource that hasn't been proven yet are the Carboniferous limestones, which are shown here in blue. These are of particular interest at the moment because they underlie a lot of the urban areas in the UK. So they could be, if exploited, provide a real good source for district heating. The potential for power generation in the UK is quite limited, and it tends to be, at the moment, the only economically exploitable resources are found in the radiothermal granites, which you see here in Scotland, in the north of England, and in Cornwall. And the most prospective granites are in fact the ones down here in Cornwall, where there's temperatures of 200 degrees have been proven at 5 kilometers depths. On the opposite scale of the temperature, on the opposite end of the temperature scale, we have mine water geothermal systems. And on the right here, I've included a map that shows you where we all have unused coal mines in the UK. So you can see them in the Central Valley of Scotland, here in the middle of England, and in South Wales. These mine geothermal systems are of great interest in the moment in the UK because they're believed to have a large geothermal resource created by the mining. And once they've been reflooded, so there's sort of potentially large geothermal reservoirs up over a range of depths accessible within these mines. Again, with the coal mine, similar to the Carboniferous limestone, what's interesting is that they tend to be in the vicinity of large cities. So you have an immediate heat customer for the resource once it's developed, which makes them obviously very attractive. And then as the fourth resource, there's ground source heat pumps, which you all know are sort of very good for geo-exchange. And specifically, we are looking at the resource beneath cities where it's a lot of heat loss from building, all sorts of subsurface infrastructure. And that's of interest to us in the UK, and how that can be used for heating. And specifically because there is no domestic cooling demand as yet. Right, so another representation of these systems, and a brief, just to show you what our current capacities are. And I think we have been looking quite sadly at the numbers from Sweden, because our ground source heat pump systems across the whole of the UK don't even add up to 40,000 as yet. So much less than elsewhere. We've currently developed, there's currently one mine water geothermal scheme under development. We have one one district heating system from a hydrothermal source, and there's two engineered geothermal systems being developed in Cornwall on the granites. Now, if you compare that to the resource, so the heat potential for the UK is estimated in the order of sort of 330 petajoules, which would be sufficient to deliver heating for 100 years across the whole of the UK. And for power, as we've seen, that's quite localized, but still there is quite a good resource there, which could locally really provide, make a difference to decarbonization of electricity as well. So I think comparing the left and the right, is quite obvious that the UK is not really using its geothermal potential and that it remains largely unfulfilled. The reasons for this is, it's been mentioned in previous presentations. Some of it is because gas is so cheap in the UK, and so it's difficult to build a business case for ground-source heat pumps, and specifically for drilling so deep wells for exploiting hydrothermal systems or build a EGS. There's a number of other reasons, including sort of the lack of awareness and knowledge about the technologies, the perceived high risk with drilling sort of deep wells, as well as the lack of sort of geothermal policies, regulations, and some discontinuity in the incentives that are being provided to support these systems. I think these are a lot of various uncertainties that hold back development in the UK. So within my research, I've with the research of my group is sort of really looking to address some of these uncertainties and challenges, and we've sort of aimed for sort of three main pillars here. The one is reducing uncertainties through improving resource characterization, through enhancing system understanding, and through developing or helping to develop policy and regulatory frameworks. I'm going to skip through a few examples. So here the first one is resource characterization. And I already mentioned that we're quite interested in the resources beneath cities where a lot of heat accumulates. And so understanding how the different heat sinks and sources interact and how that can be used for covering heating demand is one of the areas we're looking at. So urban heat, subsurface heat balances is quite difficult to do, but a very interesting research area. We've also been looking at characterizing mines, and so to develop national scale assessments of the resource. And we're tackling the carboniferous limestone, which is a whole range of research questions around that. And here we're trying to, as a first step, starting to use play fairway analysis to characterize the resource and identify further areas for a more detailed investigations. We're also really providing observatories, and due to lack of time, I'm only going to show you briefly the one that we have on mine geothermal. It's an instrumented system, including sort of distributed temperature sensing, ERT, soil gas monitoring, and a whole range of equipment to be able to better understand how mines operate and how you can use them to extract geothermal heat or cooling or use them for storage. And that's open to anyone who would like to research at the site. And I can provide further details to anyone interested. Another study, it's a whole city that we're kind of looking at is Cardiff. You've seen the picture before, but here we have loads of groundwater monitoring, loads of data on geology, temperatures, and we can use that to really understand how the city heat balance works as a whole. And then we'll have an instrumented scheme in the city, in a nursery school, where we've instrumented the whole system and the subsurface to understand the efficiency and what controls the efficiencies of these small experiments. And this brings me to my final slide, and that's really what my main interest is at the moment, is on supporting policy and regulation in the UK. We don't have bespoke geothermal policy, and there's a lot of stumbling stones. There's, we can't currently repurpose a well from oil and gas to geothermal, and there is no one really knows who owns the heat and how to regulate it. And I've we're doing a lot of science briefing paper, looking at laws and regulations around UK and what needs to change, so that we can, in the end up with the geothermal roadmap at some stage, similar to what you have in the US and what the Dutch and other countries in Europe have, but we don't. And that's the aim, is to get to a geothermal roadmap and get geothermal off the ground in the UK. Thank you very much.
All right. Thank you, Corinna. Next up, we have Frank Holcomb from Energy Security to Energy and Water Resilience.
Okay, thanks, Amy. Comms check, all good?
Yep, sounds good.
Okay, off to the races. A good day, everyone, for wherever you are dialing and connecting in from. My name is Frank Holcomb. I am a civilian employee with the Army Corps of Engineers. I'm also a researcher, and one of our jobs is to make or do research to provide innovative solutions to the problems and challenges that the Army and the soldiers have. You probably know the Army Corps of Engineers from its Civil Works mission, but we also have a military programs mission, and I'll talk briefly about that. The next slide here, if I can advance. Let's start with some history. And this is not an eye chart, it looks like one. And I actually presented this 10 years ago. So it's just to illustrate that this country has had two energy policies, Energy Policy Act of '92, Energy Policy Act of 2005. You will notice that on the right-hand side here, the slope is, increasing in the positive direction. And this is illustrated by all of the different sustainability and other policies and directives that the Department of Army and the federal government have implemented. So you may not have known or realized, but the Department of the Army actually has a lot of sustainability goals from an organization that you may not think of that in particular. So one of the major things of the Energy Independence and Security Act of 2007 was this fossil fuel energy free by 2030. And for us in the research community, that really meant getting to net zero. Net zero energy was the start, net zero energy, water and waste kind of followed. And for the water folks out there, I think it was really 2007 with this particular act that the water people got their due credit and got to be on somewhat of an equal footing with the energy folks, because energy was primarily the driving factor in the previous actions. So fast forward to the present, and now I'm not a policy guy, so I should have stated that up front. I'm a researcher. I am presenting some slides that do depict Army and DoD policy. I've cited those. But here, resilience is really the mainstay these days. So what is resilience? The Corps of Engineers has an acronym for that. It's PARA, prepare, absorb, recover, and adapt. So it's not only having secure sources of energy and water, but if there's a disruption, making it through it, obviously, with your critical missions, and responding and then adapting for the next disruption that comes along, whatever that may be. Obviously, we want to do that as efficiently and affordable as possible. And I should also say, too, that for military installations that are like small cities, it's really the critical missions that we're focused on, whether it's an airfield or a radar tower, or the mission is to deploy soldiers or to train soldiers. It doesn't necessarily mean that we have to make the entire installation net zero, but that is something that is on the minds of people. So did I just kick out Amy? Sorry about that.
Yes, you did.
Okay.
There we go.
Thank you. Moving right along. Having some challenges with, okay. So what are the issues we're facing these days? You can see here, physical, natural, cyber is a big one. There's an effort called Installations of the Future, where we want to have all the amenities and sensors and connected things that smart cities have, but that also opens up some vulnerabilities with regards to cybersecurity and people hacking in. There's a chart here that is showing that the number of utility outages is going up over time. Again, for critical missions, that is something that we have to address. And on this slide, I'm showing that the Army is interested in climate change. It's not taking any position on what is causing climate change, but it is apparent that the climate is changing and these increasing weather events and disruptive events are happening. So here, just pretty hot off the press, August of this year. There's a handbook on climate resilience that the Army published. If you're interested in getting that and doing your own resilience planning, you can download a copy from this website. And the scope of the problem here is what I'm trying to depict with this slide. You can see at the top here, there's approximately 156, there we go, 156 major Army installations, about 3 million total population. The cost for providing that energy and water, $1.1 billion annually, and about $87 million on the water side. You can tell just from that number that water is pretty inexpensive. However, there is increased attention to where the water sources are and the drought and other things that are affecting our supply. I mentioned readiness in the title. So what is Army readiness? And I actually presented this a few years ago, but readiness to the Army means having the people and trained people and equipping those trained people and having leaders to direct those equipped trained people to do what they need to do. Now, this is a little bit of a dated definition, and now as an update, installations have now been identified as one of the major tenets of Army strategic readiness. So what does that mean is that there's a recognition that for all the things that the installations do, whether it's provide force projection platforms, provide housing for the soldiers, training for the soldiers, they are integral to this notion of readiness. And providing the water and the energy required is obviously integral to that as well. General Milley on the right, back then he was Chief of Staff of the Army. Now he's the chairman of the Joint Chiefs of Staff. So he's basically the #1 military person next to the President of the United States. And he's carrying this idea of readiness with him. Right now, my abstract says that readiness is the #1 priority of the Army. That has actually been superseded as of 2 weeks ago on the 13th of October. Secretary of the Army McCarthy has basically said that people are the #1 priority of the Army, followed closely by readiness, and the third tenet or the third priority for the Army is modernization. So on to opportunities. I know I just have a couple minutes left here, but the way we look at things is that we're looking at economies of scale. And this, I think, has been illustrated by efforts in Europe, and we saw something in Sweden where district heating and cooling is a little more prevalent over there. I think we're learning from here that not every single building needs a separate system. We've, in the Army, have gone largely decentralized, but there is this notion of stepping back a little bit. If we try and look at every single building and provide a solution, we'll get one answer, but if we step back and look at clusters of facilities, we can get some economies of scale. So that includes microgrids on the electrical side, and here I'm positing geothermal district heating and cooling on the heating and cooling side. I've just thrown in a few examples here of some other campuses that are doing efforts that are pretty close by. Ball State University in Indiana has a pretty large field here, 47 buildings. I'll go to the next one. Missouri University of Science and Technology has 3 plants. Again, notice the clusters of facilities here, clusters of buildings. And even up in Wisconsin, this is a private sector corporation, Epic Systems. They do medical software and systems. You'd think in Wisconsin that they would be heating dominated, but it's actually a cooling dominated application because of all the computers, and they're basically dumping a lot of heat. They do actively manage that heat with monitoring using distributed temperature sensing, which you've already heard of, and you'll hear some more. But it's a very interesting application and a very large one as well. So this is my get off the stage chart. So sorry for the brevity here, but some of my conclusions I'd like to leave you with is that Army and DoD installations are like small cities or large university campuses, just like we have here at the University of Illinois, but they have different mission requirements, and there's some obvious other differences. Readiness, resilience, energy and water security, all of these terms sometimes are used interchangeably, but it's important to know the definitions and the differences here. And addressing these really requires holistic approaches. But it seems that microgrids, geothermal, energy storage, all of these things provide those economies of scale that we're looking for these types of things to improve the readiness at our installations. So again, the last bullet here, firmly believe that geothermal energy technologies can be a part of a holistic approach, a holistic solution to energy and water resilience, and in turn enable Army readiness. So thank you for that.